Hello and welcome to a special webinar presented by BASF. We'll be getting started in just a couple of minutes. Thank you for joining us. We'll get started at the top of the hour. This is a special webinar presented by BASF on Neopor thermal insulation. Today's special webinar on Neopor thermal insulation presented by BASF will be underway in less than 60 seconds. We have arrived at the top of the hour. I want to thank everyone for attending today. We're joined by Erin Wood, the Marketing and Innovation Manager for BASF. He's here to talk about Neopor thermal insulation. He's going to examine the relationship between home sales and insulation specs and how enhanced energy efficiency can make a significant difference on a variety of levels. We're also going to discuss the unique attributes of insulation products made with Neopor, which is a graphite-enhanced expandable polystyrene, or EPS for short. We're going to talk about the differences between traditional EPS, Neopor, and XPS, which is extruded polystyrene. He's going to talk a little bit about some case studies that illustrate the use and application of Neopor in passive house designs. A little bit about Erin before we get going. He leads the innovation and market strategy development at BASF's North American EPS foam. He's also responsible for the company's graphite-enhanced Neopor products, which we'll be talking about today. He's leading the implementation of a specification and branding strategy for insulation products made of Neopor. And as a result of efforts taken by his team, insulation products made of Neopor have been spec'd by leading architects on passive houses and LEED Platinum buildings. Erin knows what he's talking about. He's got a master's in mechanical engineering from West Virginia University and also an MBA from Case Western Reserve University. Erin, thank you for joining us today.
Thanks very much for the opportunity to talk a little bit about Neopor today. Welcome on this holiday week. I know Neopor is on the top of everybody's mind as we move into the holiday season. And also, obviously it's cold and it's winter time, so perhaps the picture of the house there on the right is an inviting a place to go visit. I wanted to present that house, or to show it on the first page here. It's our sort of our destination in the end to to kind of show you how Neopor insulation can help achieve energy efficiency and make homes more comfortable. So, well, let's get started. Slide number 2 talks a little bit about the learning objectives, which Mike covered. Again, the relationship between home sales and installation specifications is one I think that we'll find quite interesting. Then we move into the differences between some common rigid foam insulation materials and the specifications that are built around those. Next, we can talk about how Neopor is different and maybe has some unique attributes for insulation products that are made with Neopor EPS. Finally, I wanted to share with you case studies specifically for passive house designs, which is a challenging insulation energy efficiency specification to meet and requires an excellent performing material. So I hope you find this interesting, and I hope you can take something away from today's discussion. I'm certainly happy to share some thoughts. Okay, slide number 3. Just look at the relationships for, and this is perhaps viewpoints in traditional home building. 3 different views across the top of the page, one from the architect, one from the builder, and one from perhaps an economist. The architect, if we say we want to use less energy in a home, the architect will say, well, let's increase insulation thickness. The builder takes that result and says, okay, if we're going to increase the insulation thickness, then your cost to build is going to increase because we're going to use more material. Now, the economist looks at that equation and says if the cost to build increases, then obviously home sales will decrease, law of supply or price and demand. So this is really for folks who are interested in designing, building, selling, retrofitting, even moderately energy efficient buildings. This is somewhat of a problematic relationship, because if we increase or seek to decrease energy usage by increasing insulation thickness, the price of the home in theory goes up and home sales go down. Taking a little bit of a different view and flipping the view about total cost to the cost to operate, we see a different set of relationships can emerge. Again, we have the same view that energy usage, if we want it to decrease, we increase the insulation thickness. Now the builder would say, okay, if we increase the insulation thickness, but we do so cost effectively, and the cost to build is about the same, but because there's more insulation thickness, the cost to operate that building over the long term is much less, and by the way, the interior comfort is much greater. This means that now the total cost of owning and operating that building will be lower, and therefore, from the economist's perspective, if the total cost is lower, the home sales will increase. So this set of relationships, if we focus on this viewpoint, the builder view on this slide, really favors the design, build, and retrofit of highly energy efficient buildings, and puts highly energy efficient buildings in the hands of folks who are buying homes today that are at the same cost of traditional homes. So how can we have better energy efficiency? Again, the same similar builder view. Cost to build is about the same if you increase insulation thickness, but what is it truly a function of? What goes into both cost to build and cost to operate or market attractiveness? So you can see some equations here which we're going to kind of have a look at today. Cost to build, let's say a passive house, is going to be a function of really 4 things. One is insulation cost or performance. 2, mechanical costs, which can be decreased if we increase the insulation performance. 3, on-site labor, which if we choose the right insulation specification, our on-site labor and our time to build can both decrease dramatically. Secondly, market attractiveness for, let's say an example is a passive house, and really any highly energy efficient house is a function of 4 things: cost to build, cost to operate, the comfort of the interior if it's different from today's or yesterday's home, and also sustainability, which is an important part, and then growing to be a more important part of everybody's decision process. So these two functions, cost to build and market attractiveness, the argumentation here is that these two functions should be built into the installation specification. So not only the specification of how thick, how much R value, what is the ability of the material to handle water, both bulk, water vapor, submergence and water freeze thaw, but also aspects such as cost, how fast is it to install, and what is the material type. So it's interesting, if we take this a little bit further from these functions, what is the common element of all these variables? And as I kind of alluded to in the previous slide, the installation specification becomes the common variable to all of these variables in these two equations. So really what we can say, or what we could conclude, is that the installation specification is a very important part of the home building and home design process, and really can dramatically affect the market attractiveness of a specific home or building design, and therefore affect the sales of those designs. As an example, this is the Hudson Passive House in New York, designed by architect Dennis Wedlick. So here he chose walls and roofs that exceeded R50 in insulation value, exceeded an R50 wall, and chose a type, a quantity, a form, and an application that enabled that. In this case, he chose Neopor structural insulated panels for both the roofs and the walls. So for this particular project, the cost to build this passive house over a traditional house of similar style and shape and aesthetics was estimated to be about plus 3%. But the interesting thing is it's very stable interior temperatures, and 90% less energy is used to heat and cool the house. So reportedly last year, the furnace came on, or the heating system came on once during the entire winter for this particular house. So it can be seen as a successful example of how an installation specification can actually have a very cost-effective footprint, and also be a sustainable one as well. Next, I want to look at the differences between some traditional rigid foam insulation materials, EPS and XPS, and also introduce Neopor. So let me take you back to the installation specification. Here again is that sort of installation specification function. The types we're going to talk about today are EPS, expandable polystyrene, Neopor as a graphite-enhanced expandable polystyrene, XPS. The three forms we're going to focus on for today's discussion are: one, adaptable dimension rigid foam, fixed dimension rigid foam, and structural insulated panels. And then of all of the performance attributes we could talk about today, we're going to focus on three: thermal performance, water management, and sustainability. Looking at the three materials, let's take a look and see how these compare. Both EPS and Neopor as an EPS and XPS, all three of these materials are used to produce polystyrene-based foams. And these yield proven, cost-effective, lightweight, durable, water-resistant, and recyclable insulation materials. Really, there's two different processes that form these materials. One is a molded process in which the raw material is expanded by steam and infused together to make a foam. So in this case, in a molded process, the EPS and Neopor are both size and form adaptable. Both are expanded via the use of pentane in a steam and water environment, and they are closed cell molded foams. The difference between Neopor and EPS is that Neopor has high purity graphite that's added to the polymer matrix at the point of manufacture. Graphite actually absorbs and reflects radiant heat energy. That addition of graphite decreases the material's thermal conductivity, and this slows the flow of heat through the material, that increases its R value. It can be have an R value of 20% more, up to 20% more than standard EPS. Extruded materials, XPS, extruded polystyrene, are fixed dimension panels made from fluorocarbon expanded, most commonly closed, and are also closed cell extruded foams. EPS, Neopor, and XPS, from a graphical view, on the top of this page kind of describes the three different types, their forms, with EPS and Neopor EPS being an adaptable form because they're molded in large blocks, and wire cut versus XPS, which is extruded through a die and is fairly much a fixed dimension, several dimensions in terms of thickness. There's also a difference of the foaming agent. EPS and Neopor use pentane, whereas XPS commonly uses some type of fluorocarbon. The manufacturing process is different as well. The EPS and Neopor uses a steam expansion and a molding process, whereas XPS is extrusion. If you look at the chart below, this kind of shows graphically where EPS is the white bars, Neopor is the dark gray bars, and the XPS is represented as the pink boxes. Here you can see that for the density, the EPS and Neopor very much can range in density from below 1 pound per cubic foot to 3 pounds or north of 3 pounds. Because of the extrusion process, the XPS is fixed to specific dimensions which take advantage of the economies of scale of the extrusion process. R value is the next performance attribute I'd like to cover. Here you also see that the bar is wider for EPS and Neopor. This is because of the density difference between and R value. So the density of the foam has an effect on the R value of the foam. So that's why there's a range. For XPS, because of the fluorocarbon and the cell structure and the skin on the outside of the product, it tends to be a fairly confined R value of around 5 per inch. Another difference between the two materials is vapor permeability. Here we see that XPS's vapor permeability is between 1 and 1.5, and again is set per the fixed dimensions. The vapor permeability will also vary more widely for EPS and Neopor, but it's 2 to 3 times higher than that of XPS. Similarly, water absorption, as is measured in this particular test, which is I believe a 24-hour test of submerging the piece of foam into water and then measuring how much water is absorbed. The XPS has lower water absorption. EPS and Neopor also have low water absorption relative to other products such as cellulose, but there is again that range in the water absorption component. Let's take a look at the three properties: R value, performance, water management, and sustainability. First, we'll discuss R value. So this slide is a picture of R value stability over time. So this is thermal conductivity measured at 55 degrees Fahrenheit. And this is for 1.55 pounds per cubic foot rigid foam. Here we see from that XPS, if you measure it just off of the extrusion line, actually has an R value of around 8 to 8.1. It declines over time because of the escape of the fluorocarbons to the atmosphere. Fluorocarbons actually have a higher R value than air, so that's why XPS has a higher R value than just standard EPS, which is also a polystyrene-based foam. So you see over time that XPS R value decreases from around 8 to 5, in this case 5.3, because it's at a lower temperature than the standard 75 that's typically measured at. Further, over the long term, there's an expectation that fluorocarbons will continue to migrate to the atmosphere, further decreasing the R value of XPS. For Neopor and EPS, it's a very stable R value because air is the cell gas within both materials. Air is not replaced by anything other than air, so it's a very stable R value initially as measured at 6 months and over the long term. Let's talk a little bit about R value and time. Let's take a look at R value stability with changes in temperature. So this is a plot of R value both at 75 degrees F and 40 degrees F. And here we see that in all cases with all three types of materials that R value for polystyrene foam insulation increases as temperature decreases. This is a unique property associated with polymeric-based insulation. If we combine these two effects of both time and temperature, what we see is that over the time, for example, in the middle of the page, if you choose the Neopor section where at 75 degrees you start out with an R value of 4.5 per inch, and many years later, because of the stability of the R value, and it's a cold winter day, perhaps like today, and it's 40 degrees, the R value will actually increase to around 4.8 because of the decrease in temperature. So this means that Neopor performs very close to or equivalently in some cases as does XPS. Let's take a look at water management specifically for Neopor, the graphite enhanced EPS. So covering a couple different attributes. If water contacts the material, Neopor can stay in service. It does not need to be removed. It does not support mold or mildew and will not rot. In terms of bulk water, it's hydrophobic. It can be used as a water-resistant barrier. That's up to the building official, and if you use tape to seal the seams. It cannot have channels very easily and economically cut into the foam to facilitate drainage. So there's the possibility, and in the marketplace today are unique products to take advantage of this material's ability to be adaptable both in dimension and in shape. In terms of water absorption, Neopor has low water absorption with very fast release of the water gain because of its cell structure. Studies show that long-term R value performance for EPS and similarly for Neopor would be better than XPS in below-grade applications. And this is a study that was done by the EPS Industry Association. Water vapor permeance, again, back to the chart I mentioned before, EPS and Neopor are 2 to 3 times more permeable to water vapor than is XPS. This means that in a condition where there's condensation on the back of the wall, we can move that condensation out faster with a more permeable material. So as insulation becomes thicker on homes because of energy codes, Neopor is, because its R value is higher than EPS, an excellent choice to replace XPS in walls in below-grade applications. Additionally, when we look at freeze thaw cycles in ice, the industry studies have shown that there's no negative effect on the thermal performance of EPS, and similarly for Neopor, that would be as classified as an EPS, that would be a similar situation. In terms of sustainability, Neopor is Green Guard certified and also Green Guard certified for children in schools. It is a resource-efficient material. It uses steam in a relatively low-energy process, and steam is often recaptured as water and recycled for further use. Pentane as a foaming agent can actually be captured and reused as fuel to generate steam for the same process that expands the material. And as I mentioned, water can be collected from the steam and reused many times. Neopor has the ability to be recycled, and it can contain recycled content. Because it's a plastic-based or polystyrene-based material, it can be reformed into another product, a picture frame, a plastic part for another industry. It's also environmentally friendly in the sense that there's really no land degradation due to quarrying for raw material. It doesn't contribute to any deforestation or destruction of plant life. It does not contain any fluorocarbons or formaldehyde. And it's also inert, stable, and does not produce any methane gas or leachates that contaminate the material. Or sorry, contaminants that leach from the material. In addition, the carbon footprint and the sustainability aspect for Neopor is very interesting. Versus both its similar materials, EPS and XPS. For Neopor, because pentane is the foaming agent, Neopor has zero global warming potential. This makes it quite different from a fluorocarbon expanded XPS. In addition, because it has a long-term stable R value, that can dramatically improve the energy consumption in buildings with long-term versus materials which decline over time with R value. Additionally, energy payback, for many materials, including Neopor, can be as little as 1 year, depending on the climate zone. And EPS is manufactured locally, so this means that there are more manufacturers for EPS than let's say, an XPS. So the material will be closer to the job site, which reduces transportation costs, fuel loads, and those types of things, and makes it an overall more sustainable product. So I hope I covered some of the differences between EPS, Neopor, and XPS. There'll be an opportunity at the end we'll take some questions, and we'll try to answer those questions. I'd like to share with you now some of the unique attributes of insulation products that can be made with Neopor. So just as a summary, there's really two types of Neopor when we think about it. If we go beyond Neopor EPS, which is sold by BASF to molders that then take EPS and turn it into foam insulation. When we talk about Neopor as a foam, we see it has really 6 characteristics. 1, it's sustainable. Number 2, it has a relatively high and long-term stable R value. Makes it perfect for space-constrained applications. It's also Class 3 vapor permeable. It has adaptable density and dimensions. So it can be really almost any density between 1 and 3 pounds, and can be made in blocks up to 16, 20, 24 feet long by 4 foot tall by 4 foot wide. It's dimensionally accurate. Wire cutting of Neopor is a bit more accurate. The molders prefer to cut Neopor. Some molders prefer to cut Neopor over white because the graphite aids in the dimensional accuracy of this cut. It's also a very cost-effective material. If we look at finished goods made in Neopor, and I know Mike at the beginning mentioned the brand management. Neopor is available, I should say finished goods made of Neopor can be identified by the Neopor trademark, and that's used as an ingredient brand on those products. So the ingredient brand is the industry's assurance that the product contains Neopor and abides by certain quality guidelines as part of a network of molders that produce these products. As part of that, Neopor has consistent quality, so it's actually manufactured under a brand marketing agreement with guidelines and specifications for foam quality, for performance claims, and for trademark usage. So of the materials in the marketplace, Neopor is quite unique in terms of those attributes. So to think about some of the applications or where Neopor can fit into insulation products, as I mentioned, it has very adaptable performance. So we find it being used in board stock and ASTM Type 8, Type 2, and Type 9, above grade, below grade, in east systems, and in stucco. It's used today in insulating concrete forms, structural insulated panels, window frame inserts, and that comes back to the wire cutting. It's NFRC rated. Door cores, also companies have developed specialized remodel and retrofit products for both interior and exterior use. It has a use in insulated headers, which again is a space-constrained application perfect for a stable high R value material. It also finds use in medical packaging and cold shippers. If you'd like to find out more about where to buy Neopor, just visit our website at www.neopor.basf.us. Next, I wanted to cover some case studies, use and application of Neopor in some passive house designs, and I hope you find this to be of interest. This slide shows the Hudson Passive project. This is the house in New York, designed by Dennis Wedlick Architect, built by Bill Stratton Builders. As I mentioned before, R values of over 50 in the walls and roofs, achieved by a 12.25-inch Neopor structural insulated panel. What's interesting here is that the 12.25-inch thick SIP could have easily been white, but it would have been 14.5 inches thick. So in this case, once we get to the level where Neopor, where the insulation value needs to be high, Neopor really begins to shine, to reduce that thickness, to make it more economical to use a thinner panel. This is another passive intent residence in New York, again by Dennis Wedlick. Here we see this is Neopor being used as perimeter insulation. This is a 1.35 pound density product. It's fairly thick, which makes it an excellent place to put your tools. It's also, interestingly, a monolithic block, meaning it's 10 inches thick and it comes that way. So there's no need to laminate multiple 2-inch sheets together. It can be one 10-inch thick sheet. That makes it a lot easier to install and a lot faster. At this density, the R value per inch will be about 4.55 per inch when measured at 75 degrees F. Very dimensionally accurate to 1/32 of an inch or 16 feet. Here we see it's sealed with polyurethane to meet the passive house air exchange requirements. Next, I wanted to share with you structurally insulated panels. These are graphite-enhanced EPS SIPs that offer lower total cost. You can see some of the benefits here, and this table compares in the middle a 10.25-inch SIP or a 10-inch structural insulated panel mated with a Neopor core to a 12.25-inch on the right-hand side white EPS core. You can see that the R values are very similar. Neopor is perhaps 1 R less, but the value of what Neopor brings into this application, if you needed a 12.25-inch SIP for your design and your energy specification, are apparent in this table. So now the structurally insulated panel becomes thinner and lighter, so you can it's easier to handle, faster to install. The efficiency of handling is much greater. The efficiency of transporting those panels is higher. The SIP weighs less. And interestingly, the roof line is thinner, which means now you can cut the trim cost, and the dimensional lumber that you need to support that is much less. So here's some pictures of these panels in operation and the construction of the home in New York. Again, it's a monolithic block. For the same R value, they're getting thinner walls and roofs, and really the best installed cost option versus EPS and XPS. If your specification requires, structural insulated panels with a high R value. This home was pretty interesting. Achieved a very impressive 0.1 air changes per hour. The last case study I wanted to share with you is a Habitat for Humanity home in Columbia County, New York. Again, Dennis Wedlick is the architect on this home as well, or on this multifamily residence. Here, Neopor is being used in 4-inch thick pieces with overlapping joints as both an interior perimeter insulation for the basement and also below the slab. So we got some feedback from the workers on this particular house The workers found that they could walk on the surface without cracking that surface, from what they said was due to a lack of skin on the Neopor. Again, it's wire cut, so it's a very consistent, smooth, and durable surface to the material. It's durable and easy to install at a nice density of 1.35 pounds per cubic foot. And if you like silver gray, this is a beautiful color, and it's less costly than XPS in this form. So that kind of covers today's, I guess, presentation about Neopor. To learn where you can find out more, just simply write to us at the address on the screen, neopor-us@basf.com.
Thank you, Erin. I appreciate that. We do have one question from the audience. Robert asks, are the channels for the water drainage, when you were talking about that portion of the presentation, are they cut or are they molded in during the manufacturing process?
They can be both. Neopor and EPS can be both block and shape molded. So it is possible to construct a mold and to what the industry calls shape mold the product, where the beads come out and there's just one shot, and the part comes out with it formed into the shape of the mold. The other way is to wire cut the channels. And here you'd have a block, and the wire would simply move through the solid block of foam, cutting the channels. And oftentimes this is designed so that one piece is a mirror image of the other, and there's no scrap to achieve that. So it depends on how the finished goods supplier or the manufacturer wants to set up their operation and what their design goals are for that. But the Neopor is capable of both.
Okay. I had a question or two as well, and if it sparks other questions from the audience, that's fantastic. We'll take them. You had mentioned that Neopor was used in the ICF manufacturing process. That's correct?
Yes, that's correct.
Okay. I know that they also make ICS out of EPS and XPS. My question isn't so much about that, but it is about a specific concern that is prevalent sometimes in the construction process using ICS, and that is termites. I know that some ICF manufacturers had gone to treating their forms with borate to try and repel termites, but given that this is infused with graphite, I didn't know if you guys had any research on its, I'll call it inherent termite resistance. Do termites find that they don't necessarily like chewing on any kind of graphite at all?
Yeah, I don't know if we've actually conducted any research into termites either being attracted to or repelled from, graphite or graphite as contained in foam, in EPS foam. But we haven't seen any negative effects, worldwide since the product was introduced in 1995 of any effects of termites being attracted to a Neopor foam or conversely repelled from it.
Sure.
We do see in the industry that companies do add borate and also Preventol, which is a product from Lanxess as a termiticide to Neopor.
Okay. We have a question from George. He wants to know where the Neopor is manufactured.
Neopor is manufactured both in Korea and Germany.
Okay. And Roland had a question. He apologizes if you've already covered this, but the STC rating for this material, and also as a follow-up to that, is there a place where he can find that kind of data for other BASF products?
Sure. The FPC rating, I'm not sure what that is offhand, but if he would write to us at that email address, we can address that question. And
the sound transmission is what he's looking for, the sound transmission rating.
Yeah, I don't recall offhand what that number is, but we can certainly share that once we have some time to look it up.
Okay. All right. I had one more question for you, and that was there's a lot of discussion about R values, certainly very prevalent in the industry, referenced in codes. But I had a question. Was there any data available on U values, which is the inverse of the R value? And it's kind of, for those who aren't aware of U values, they measure the overall heat transfer coefficient.
Yes, U values are available, I believe, from we don't usually run into those so much here, but I think they are available in literature from our European colleagues. And if our website, neopor.basf.com, will take you to a selector in which you can find the different countries and then track back into, and we can certainly provide that information too, from a question posed to the email address I mentioned before. And I'll also add that we've characterized Neopor, both the standard product and also a follow-on product that has even higher R value. It has more graphite in it than standard, so it exhibits a higher R value than what's what's commonly used. Both of those products are going to be listed in the NFRC National Fenestration Rating Council guide, and I believe the U value is an output of that work.
Okay. Yeah, certainly U values aren't referenced in code, I don't believe, and they're not talked about too frequently, at least in the U.S. But that was more just for those who are, I'll say, very passionate about energy efficiency and building science. So that's why I asked the question. I don't see any other questions in the box there. I want to thank Robert and George and Roland for asking their questions, and obviously Erin for your time as well, explaining all about the Neopor thermal insulation product.
Thank you. I appreciate the time and appreciate everybody's attendance, and hope everybody has a great holiday season.
Thank you. Take care.
Bye.